This is a discussion on the material in section 3.3. And so, in section 3.1 and 3.2, we talked, we discussed how to get a derivative um, uh, using, using limits. And, we had that rule limit of f of x plus h minus f of x over h. And, we found that, sometimes it was difficult. We had to multiply by the conjugate, or we just had to or maybe reduce a rational expression to make sure that the denominator did not have a factor of h, because we can't divide by 0. So now we're actually going to learn some rules here that'll make life a little bit easier. And the problems actually get more, we get word problems and they're more challenging, but at least every time, when you calculate a derivative, you don't have to actually go through that whole process of, multiplying by the conjugate and doing a lot of algebra. Okay, so the first rule is that the derivative of a constant is 0. Okay, so if you think of the derivative of the slope, well, we know the slope of a constant line is 0, y equals 3 or y equals 4. There's no change. There's no slope. It's just this flat line. Okay, so here's another one. I'm going to actually talk about this a little bit more below, or try to give some motivation for it. With the power rule, real, very useful rule. And some of you noticed that when you take the derivative, let's say you're taking the derivative of x to the n, and in this case, n is actually just, can be any number here, but so the derivative of x to the n is n times x to the n minus 1. So we drop down the exponent and we subtract 1 from the exponent. And we'll look at some examples in a minute. Actually, I just wanted to talk about this just a little bit. So this isn't a course on proofs, and you don't have to know how to prove this, but I did do a kind of, hopefully my writing is okay. At the very bottom, I did a little bit here. Okay, and so one thing is, I'm assuming in this case, let's say n is a positive integer, because what I'm going to use is this rule, the binomial theorem, which you can actually look up. It's a way of expanding. We know how to expand like x plus y quantity squared, and you might even know some quick rule for expanding x plus y to the third power. Now, what about x plus, h raised to the n power? So here is the definition right here. So here is the definition of the derivative, right? So it's x plus h to the n minus x to the n all over h. And so in this case, my function is f of x is equal x to the n. I want to take the derivative of f of x equals x to the n, where in this case, I'm going to assume n is a positive integer. And so, yeah, so there's the derivative function. So you think that, well, how do I expand x? You have to expand x plus h raised to the nth power. And then there's this famous binomial theorem, which actually is n plus, if you expand x plus y squared, there are 3 terms. You expand x plus y cubed, there are 4 terms. We expand x plus h raised to the n, there's actually n plus 1 terms. Okay, so, and the only term that's actually going to matter, as it turns out, it's going to be this one, the one that I just underlined there. Okay, so, and so x plus h to the n, using the binomial theorem, is x to the n raised to the n power, and then it's n times x to the n minus 1 times h. And then the next term is n times n minus 1 over 2. And these are called binomial coefficients, but let's and then look at the term. It's x to the n minus 2h squared. So if you add the exponents, you always get n. And the next one is n times n minus 1 times n minus 2 over 1 times 2 times 3. And now you subtract 1. Now it's x minus 3 h cubed. So notice it's x to the 1, x to the n, h to the 0. And then it's x to the n minus 1 times h to the 1. We subtract 1 from the exponent of x and add 1 to the exponent of h. And eventually you'll get you'll get at the end n times x to the first, h to the n minus 1, and then plus h to the n. Okay, so that's x plus h squared. And then you're going to subtract off x to the n. Okay, so what's left? Every other term has some factor of h in it. Okay, so x plus h to the n, and then you subtract off x to the n, we're right here, and then you get n times x to the n minus 1 times h, and that's h to the first, right? And we're going to be dividing by h. So then it's plus n times n minus 1 over 2, x to the n minus 2h squared, and so forth. And then you're going to divide by h. And so what's going to be left? You're going to get n times x to the, yeah, see the h term cancels. That first term, the h goes away. N times x to the n minus 1 plus n times n minus 1 over 2, x to the n minus 2 times h. Now all the terms add up, the exponents add up to n minus 1, then plus n minus 1, n minus 2, over 1 times 2 times 3 times x to the n minus 3 h squared, and so forth. But all the term, there's only one term that's not going to have an h in it. So when h goes to, it's this one right here. It's the one that I just circled. That's the only n times x to the n minus 1. And so then as h goes to 0, that's the only term that's left. Yeah, so that turns out to be the derivative. The derivative, so here's the derivative of x to the n. The derivative of x to the n is n times x to the n minus 1. And it's all because of the binomial theorem. Okay, well, so much for that. So that's the only proof I'll talk about right now. Again, if you're a math major, you probably take a course where you talk about this in more detail. Okay, so now, so the derivative of a constant is 0. The famous power rule, which is really quite useful. The derivative of x to the n is n times x times x to the n minus 1. And definitely something we want to memorize. Then if you multiply, the derivative of a constant times f of x is the constant times the derivative of f. So we can actually pull that constant out, right? So the derivative of c times f of x is c times the derivative of f, which is really quite useful. So like you want to take the derivative of, like, here's an example. You want to take the derivative of 3 times x to the 5th. Well, it's just 3 times the derivative of x to the 5th, or 3 times 5 times x to the 4th, or 15x to the 4th. Now here's one. And we actually had a problem where we had x, the square root of x in the denominator. And there was a lot, I think I mailed it out to the class, or I posted it online. And now you'll see, oh, look how easy it is now. Well, now that we have this theorem here, this fact. So let's look at example 3 here. Y is equal to 2 over 5. 2 is the numerator and 5 square root of x is the denominator. 2 over 5 times the square root of x. And again, so the constant is 2/5. And we'll write the exponent. We'll write 1 over the square root of x is x to the negative 1/2. And now we can use this rule number 2 right here, where we drop down the exponent, negative 1/2, right? We drop down the exponent of negative 1/2, and we subtract 1 from the exponent. So we get 2/5 times negative 1/2 times x raised to the negative 3/2, or negative 1/5 times x to the negative 3/2. And so that was a lot. So if you actually looked at that document I posted online, just a lot of steps, lots of algebra. Of course, with lots of algebra, lots of room for error, isn't there? Okay. So now it's like we can't stop doing this, right? So it's like now that we want to do the power rule all day long. Okay. Example 4, we have this, when you add, so the derivative of the sum, this is rule number 4. The derivative of the sum is the sum of the derivatives, right? The derivative, so let's say you want to take the derivative of f of x plus g of x. It's equal to the derivative of f of x plus the derivative of g of x. So, some people would say, I guess maybe I'm one of those people. So some people, including me, they say that the derivative operator is linear. Okay, so it's not really think of it, there's not too many rules where you can say, oh, the derivative of f of x plus g of x is the derivative of f of x plus the derivative of g of x. It's not, it seems kind of like, oh, that's whatever. But look, there's not too many rules like this. This is not true. Sine of x plus y is not equal to this. See, it's not too many things that are actually linear like that. So this is, students says, yeah, so the sine of x plus y is not equal to the sine of x plus the sine of y. So linearity, this kind of linear operator is not something that really happens a lot in math, but the derivative function is. So the derivative function is linear. The derivative of f of x plus g of x is the derivative of f plus the derivative of g, which kind of makes life easy. Because now, I'm going to erase this because I didn't want to look at this. Okay, so because let's say we want to take the derivative of a polynomial, we can just take the derivative of it term by term. Like we have this function, 7t cubed minus 5t squared plus 3t plus 1. And now we can just take the derivative of each individual term, right? So like 7t cubed, right? And then so it's 7 times, we drop down the 3, and it's t, and then we subtract 1 from the exponent, we get 2, and we get 21t squared. And you can do the same thing for minus 10t. The derivative of t is 1, and the derivative of 3 is 0. Oh, I'm sorry, I'm looking at the derivative function. The derivative of 5t squared is, yeah, we drop down the 2, and we get minus 5 times 2, so we get minus 10t. The derivative of 3t is just 3, because and the derivative of 1 is 0. Okay, so and so yeah, so again, we can do the same thing, same, even more complicated exponents. We did x to the negative 1/2. So if you look at this example 2 here, we have 8 times x to the negative 2 plus 3 times x to the 2/3 power. And so yeah, so again, so you just drop, like here, you just take the derivative of 8 times x to the negative 2, you drop down the negative 2, so 8 times negative 2, you get negative 16, and you subtract 1 from negative 2 to get negative 3. The derivative of x to the 2/3, it's 2/3, you drop, so it's 3 times, 3 times 2/3 times x to the negative 1/3. It's really, yeah, it's really great. It is great. I mean, we don't want to do f of x plus h minus f of x over h for the rest of our lives. So, okay, and here's just a few more examples that I think you can do. Definitely derivatives of, here's like a and b are derivatives of polynomials. So you just take it term by term. And the important thing is that so here it's easy, like in a and b, the exponents are positive integers. Okay, so let's look at d. Just make sure, just write the, here the variable z, and c is in the denominator. Just make sure the variable is in the numerator, and the exponent might be negative, or it might be a rational number. Yeah, so the derivative of like 3/4 to the 3/4 times z to the negative 5. Again, it's, you just drop down times 5, and you subtract 1 from negative 5, and you get negative 6. All right. And then typically, yeah, in the end, you don't want to write the answer with a negative exponent. So if you see there at the end, it's negative 15 over 4 times z to the 6. And here's just some more problems with exponents. I think we can all do that, or I shouldn't say we can. If you can't, then I think anyone can learn it if they're interested, and if you're having a hard time, make sure you can contact me. So okay, so we're actually going to learn, okay, so here, let's look at f and g. Okay, so you actually have the first one, g of t is 5t cubed minus 4 square root of t over t squared. So we're actually going to learn a rule called the quotient rule, where we wouldn't have to simplify. I still would simplify. I wouldn't use, this quotient rule I think is actually harder than what you see right here. We're just reducing the fraction, so 5t cubed over t squared minus, let me see, we have this function, 5t cubed minus 4 square root of t over t squared. And now we're going to simplify, we're going to separate the terms. So it's 5t cubed over t squared minus 4 square root of t over t squared. And now just use the law of the exponents, right? So like 4, we have t to the 1/2 over t squared, and you just subtract, so it's 1/2 minus 2. You see here now you get the minus 3/2. And then t cubed over t squared, you get t. So we just use the law of the exponents, and we actually simplify g, and you get 5t minus 4t to the 3/2. And now you can actually take the derivative. The one thing be careful about, students, and it's a really common error, see how you have the minus sign here and the exponent's negative. So when you drop down negative 3/2, it's minus negative 3/2. It's going to be, that becomes positive, and then you multiply it by 4. And that's how you get the 6. But the important thing here is that we get the correct sign. Here, now students, in G, we're actually going to learn a rule called the product rule. But right now we don't have it. And again, here it might just be just as easy to expand. This is G here, we have that product. So just expand the product. We can use our friend FOIL or distribution. So, and so, but yeah, here, so right now, with what we know right now, we would have to expand that first. We'd have to expand the function at m first, and then take the derivative term by term. Now, some of this is, we saw, okay, so now we can just do the same types of problems that we did before. So you have this function minus x cubed, I'm looking at problem number 2 here, plus 7x squared, plus 5x minus 1. And we want to know the equation of the tangent line at x equal 1. Okay, so first of all, we know you plug in 1, and you're going to get f of 1 is 10. So yeah, negative 1 plus 7 plus 5 minus 1 is 10. So that function, this function f goes through the ordered pair 1 comma 10. And we want the slope. And again, now you just have to find f prime of 1. Now, okay, so we don't have to take, even under the way we were doing it before, using taking the limit of the difference quotient, finding a derivative of x cubed, would be a certain amount of, not, after a while you do these expansions, it's not too hard, but you'd have to remember, okay, how to expand x plus h cubed. But now we really don't have to do that. We just use this power rule. And so the derivative of minus x cubed plus 7x squared plus 5x plus 1 is you get minus 3x squared, and then it's 7 times 2 times x. The derivative of 5x is 5, and the derivative of 1 is 0. And now just substitute 1, f prime of 1 is minus 3 plus 14 plus 5 is 16. So the slope is 16. And so we want to find the tangent line of this function, minus x cubed plus 7x squared plus 5x minus 1 at x equal to 1. We know it goes through 1 comma 10. And we just calculate the derivative, and then we find f prime of 1. We find out that that's 16. So yeah, so here's the equation of the tangent line right here. Y minus 10 equals 16x minus 1, and this isolate y. Yeah, you get y is 16x minus 6. Yeah, and just plug in. If you substitute, if you look at this tangent line, you substitute in x equal to 1, yeah, you're going to get 10. You want to make sure that the tangent line intersects the curve, at the point. We know that the curve goes through 1 comma 10. We want the tangent line that goes through 1 comma 10. So just verify that your final answer, that the point that you're looking for, that we're trying to find the tangent line for, actually goes through the line. So here, number 3 is, we're actually going to be doing this a lot. So find where the curve in problem number 2, and that's that, it's that same function, minus x cubed plus 7x squared plus 5x minus 1. We want to know where it has a horizontal tangent line. So in other words, so it has a horizontal tangent line where change, a couple places, like one place is where it potentially changes direction. There's another time where it's called, there's like a point of inflection here, but let's say we have some curve like this, and we can see, yeah, whoops, my tangent line's terrible, but you can see that where the curve, that curve changes, it goes up and all of a sudden it hits a peak and then goes down. That's where it has a horizontal tangent line. The slope is 0. Yeah, so you just actually solve the equation. We have the derivative minus 3x squared plus 14x plus 5. You set it equal to 0, and this solved that quadratic equation. So it actually, it's set up so it factors really nicely right here. And yeah, so you get it x equals negative 1/3 and x equals 5. The derivative is 0. So at those 2 points, it's a good chance that the function just changes. Well, the function will have a horizontal tangent line. Okay, we'll talk more about rate of change a little bit later in this course, but yeah, so we'll see that the derivative, kind of, if it's a physical quantity, let's say we're talking about speed, or that the derivative, maybe we're talking about change in distance with respect to time, that the derivative can be a velocity. So let's say if you have some function, like some distance function, like in physics, you throw a ball in the air and you can kind of measure how high up it goes. You may have learned that, something like that in your physics class. So the derivative of a distance function is velocity. It represents a rate of change. But that's kind of a coming attraction. We'll do a lot of problems like that. Oh yeah, we will do more application of rate of change in section 3.6. Oh, that's not too far away. Wow, I think it's next week. All right. So okay. And then higher order derivatives. And yes, we will Well, we'll have problems where we're actually also looking at the a secondary. We're going to look at the rate of change of the derivative, and that'll give us the acceleration. So not only will we see, is the slope going up or going down, how is the derivative changing? Is the rate of change increasing or the rate of change decreasing? So if the rate of change is increasing, that means that your function's going faster at a faster and faster rate. So it's like when you're accelerating, you put your foot on the gas pedal, or you're decelerating, you're putting your foot on the brake. The velocity is slowing down at a faster and faster rate when you really push down on the brake pedal. Okay, and then I think that's all for right now.